Hello, my name is Grace Lee and I'm an undergraduate research assistant in Professor O'Brien's lab at UC Berkeley. During my summer at Pixar, I had a chance to listen to Director of Lighting for Toy Story 3 talk about the challenges of lighting a nighttime scene. Nighttime scene is one of the most difficult scenes to light for lighting artists, and it's because the lighters need to tell a story through lighting cues. And this requires non-physically realistic lighting that may accentuate a certain character or use a certain color to communicate the mood of the story. And it's challenging to maintain the believability of nighttime scene and still guide the eye to the main point of the story. Nighttime lighting is also difficult because the reference images the lighters use to match the lighting in their shots are often perceptually inaccurate. Unfortunately, many of the nighttime cues the human eye perceives become lost when captured with a camera. This is because there's a nonlinear color shift in the eye in low light environment that is not modeled by the camera. For example, this troll image shows a camera output that didn't take into account the perceptual color shift that happens at night. Whereas this tone-mapped image does take into account the nonlinear color shift. By nonlinear color shift, what I mean is that during daytime, the human eye uses long, medium, and short, aka LMS cones, to sense the light in the scene. These values are then turned into what is called an opponent color channel, which is then sent to the brain. In nighttime, rods become more active than LMS cones. These four signals get mixed into opponent color channel in a nonlinear way, causing color shift to happen during nighttime. Because display devices don't account for the rod response, it fails to take into account the color shift that happens in low light environments. Because cameras are not adapted for nighttime shooting, what ends up happening is that the artists at production companies have to color correct the images, and often what they do instead is to capture the scene during daytime and tone map it to look like a nighttime scene. Sometimes directors stylize a scene to a great deal like this image from Sucker Punch. So the tone mapping tool needs to be flexible for these stylization choices. My work focuses on building an efficient and intuitive tool for artists to tone map their low light scenes so that it represents perceptually plausible low light scene, while still flexible enough for artistic control by the artists. Our system also needs to be able to tone map both live and virtually rendered frames, and do this in real time at the artist's command so they can iterate. Much of the nighttime tone mapping work is outlined in Kirk and O'Brien's Perceptually Based Tone Mapping for Low Light Image paper, published in SIGGRAPH 2011. Here are some of the results from their work. My work extends this algorithm to video, but there are several challenges. Their pipeline requires spectral image as an input, which is an image that contains spectra of light absorbed at each pixel. The process of accurately generating spectral images often requires capturing the scene using multiple filters and then solving for the spectral distribution of each pixel. Their method is also written in MATLAB, so it is too slow to tone map the frames for video. Time coherence is also a potential problem that hasn't been solved yet, and their pipeline is not designed with artists in mind. For our system, we decided against accurately generating a spectral image, because there is no way to capture spectral video with commodity hardware. Instead, we plan to take an image in RGB format, which is far more common, and transform it into LMSR, long, medium, short, and rod space, by hallucinating the rod response. Kirk and O'Brien's paper does include a section on estimating LMSR image from RGB image, but it shows poor approximation except at the low light images. And they get around this by blending the tone-mapped image with original RGB image. Part of our work is verifying that we can do a better job in approximating the LMSR values than Kirk and O'Brien. More importantly, their system doesn't provide any way for artists to adjust the final output. Since our tool estimates the rod response anyway, we can further adjust the curve that we fitted such that it meets the artistic needs. So for a moment, let's assume that we can generate a spectral image dataset. We can then categorize these images into different lighting environments such as sunset, fireworks, etc. We can have the user specify a dataset that best represents the input video. Then we can pull up the basis spectral images that we calculated from averaging the images in this category of the dataset. From these basis images, we can construct a spectral estimation of the input image. After converting the RGB input to spectral, we can now tone map the images using a real-time system. The UI displays the LMSR spectral intensities of the image, as well as what the image looks like in daytime, which is photopic, and in mid-range, which is also known as mesopic, and at nighttime, which is also called scotopic. The artist can decide to alter a color of an object in the image using a paintbrush tool. The system then recalculates the LMSR and other values so that it becomes more perceptually accurate. Thank you for listening, and I will take questions.